Okay, let's dive in. Imagine your clothes doing more than just, looking good or keeping you warm.
Hmm.
What if they could actually sense your body's signals, power your gadgets, maybe even light up?
It sounds like science fiction, doesn't it? But it's really happening.
Exactly. This isn't just futuristic fantasy. It's the exciting reality taking shape in the world of electronic textiles. E-textile.
That's right. We're talking about seamlessly blending electronics.
Hmm.
Things like sensors, power sources, maybe even tiny processors.
Right into the fabric.
Directly into the fabrics, the yarns, the fibers themselves. It's a fascinating fusion of two very different worlds, really, textiles and electronics.
And today we're doing a deep dive into this cutting-edge field. We're using a recent, pretty comprehensive review paper to guide us.
Yeah, it pulls together a lot of different threads, so to speak.
Huh, nice one. So our mission today is to unpack what this source tells us about the materials being used, the ways these smart fabrics are actually made, and this is really critical, how do we make them sustainable?
That sustainability question is huge because, let's face it, both the textile and electronics industries already have massive waste challenges.
Exactly. So we want to cut through some of maybe the denser technical details in the source.
Yeah, get to the core idea.
And really understand what's genuinely possible today. What are the biggest roadblocks researchers are hitting?
The challenges, yeah.
And how this technology is sort of confronting its potential environmental footprint. We want to give you the essential knowledge, the takeaways you need to understand this rapidly evolving space.
Right, so you can follow along as things develop.
Okay, so let's start with the basics. What exactly is an e-textile at its heart? And, why is this area getting so much attention right now?
Well, at its core, an e-textile is certainly a textile fabric, yarn, whatever, with electronic functions embedded within it.
Embedded, okay.
Yeah, integrated. So this could be anything from sensing things like your heart rate or movement to actuating something, maybe creating a small vibration or a light-up display.
Oh, cool.
Or even processing data, communicating wirelessly, all integrated directly into the fabric itself.
And the reason it's such a big deal, textiles are everywhere.
Exactly. Ubiquitous is the word the source uses.
Yeah.
They're everywhere.
Yeah.
So this opens up the possibility for ubiquitous deployment of technology.
Putting tech anywhere textiles are found.
Think about the potential. Smart, everyday clothing, high-performance sportswear that monitors your form.
Yeah.
Healthcare garments, tracking patient vital signs. Workwear that enhances safety or communication. The applications are potentially vast.
And the key technical goal, I guess, is to do all this without ruining the feel of the textile.
Absolutely. You want to integrate these electronic capabilities while preserving the properties we actually like about textiles.
Flexibility.
Comfort, breathability, being lightweight, durable. The course even mentions using strong technical textiles, like those in bulletproof vests or geotextiles, as potential starting points.
Right. And this is a big step beyond, those early hobbyist kits, isn't it? Where you'd maybe sew a rigid circuit board onto fabric, like the LilyPad Arduino.
Oh, definitely. The source highlights that the real engineering challenge now is achieving seamless integration.
Seamless
integration that not only works with high-volume textile manufacturing processes, weaving, knitting,
re-industrial scale,
but can also survive the demands of real-world use. And a big one there is washing.
The washing machine, the enemy of electronics.
It really is. Machine washing is surprisingly harsh. Making these integrated functions durable enough to withstand repeated wash cycles is, well, it's one of the major hurdles for widespread adoption.
Okay, so how are people actually building these smart fabrics? The source seems to cover two main paths. First, putting the function right into the yarn, and second, applying materials onto the fabric surface, like printing. Let's start with the yarns, working with functional yarns.
Yeah, this approach is really appealing because yarns are the fundamental building blocks of textiles, right? So if you integrate the functionality there, it's naturally compatible with standard textile processes, weaving, knitting, embroidery. It helps the final fabric keep its flexibility, its drape, its textile feel.
And I guess the most basic function you need in a yarn for electronics is conductivity, making it carry electricity.
Absolutely. Conductive yarns are fundamental, and engineers have several ways to create them.
Like what?
Well, they can use very thin metal wires, like superfine strands of stainless steel. Or they can take standard textile yarns, polyamide, polyester, and coat them with a conductive material. Silver is pretty common.
Coating them, okay.
Or you can blend metal fibers directly with textile fibers before spinning the yarn. Or, interestingly, you can use certain polymers, plastics, basically, that are inherently conductive themselves.
Oh, right, conductive plastic.
Yeah. The source mentions there are commercially available options, like silver-coated polyamide yarns that researchers can just buy and use.
So once you have these conductive yarns, how do you actually get them into a piece of fabric?
You can integrate them right during the fabric creation process. So in weaving, they can replace standard threads in the warp direction, or the weft, or both.
Like swapping out some regular threads for conductive ones.
Exactly. Knitting is also really versatile. You incorporate the conductive yarns into the loop structure. This can produce soft, stretchable conductive areas, and it's relatively quick for prototyping designs.
And what about embroidery? That seems different, like adding it afterwards.
It is. It's an additive process. Automated embroidery machines are increasingly used to essentially draw conductive paths or patterns onto existing textiles using conductive thread.
So you need conductive thread for both the top and bottom.
Often, yes, for good conductivity. And the source points out something interesting for connections. Ultrasonic spot welding.
Welding on fabric.
Yeah, it's proving to be a reliable way to make low-resistance electrical connections to these embroidered conductive yarns, where you need to connect something else, perhaps.
Okay. So with just these basic conductive yarns, what kind of simple electronic elements can you actually create right in the fabric structure?
Well, you can make components that just rely on having a specific conductive pattern. The source gives examples like radio frequency antennas for communication.
Like for Bluetooth or something.
Potentially, yeah. They showed an example of embroidering conductive threads in a specific shape, like a bow tie, to make an antenna. You can also create simple conductive tracks to act as wires within a textile circuit.
Just routing signals.
Exactly. And they also discuss woven and knitted structures acting as sensors themselves, like a knitted fabric where the conductivity changes as it stretches.
Oh, a strain sensor.
Right, or a woven fabric designed so that pressure changes its resistance, a pressure sensor.
And I saw a note in there about coils for wireless power.
Yes, that was a neat finding highlighted in the source.
Yeah.
A study compared different ways to make coils for wirelessly transferring power.
How'd they make them?
They tried standard embroidery with conductive thread, they tried printing with conductive ink, and they tried a technique called couching.
Couching?
Yeah, it's an embroidery technique where you basically stitch down another, often thicker, thread onto the fabric surface. In this case, they couched down a special multi-strand conductive wire called Litz wire.
Litz wire, okay. And what did they find?
They found that the couched Litz wire method resulted in coils with the lowest electrical resistance.
Which is good for power transfer, right? Less energy lost.
Exactly. Lower resistance means higher efficiency when you're trying to get power wirelessly from one coil to another without losing too much energy as heat. It actually outperformed the coils made just by printing or simple embroidery in that study.
Interesting. Okay, so conductive yarns are foundational. But the source also talks quite a bit about advanced functional yarns. What does that mean? Going beyond just carrying current?
This is where it gets really interesting, I think. Advanced functional yarns integrate more complex capabilities. Sometimes this involves multiple material layers coated onto the yarn, or even embedding tiny electronic components directly into the yarn structure before it's even knitted or woven.
Whoa, components inside the yarn?
Yeah. These yarns can actually do things like harvest energy from the environment or store energy.
Building tiny power sources or batteries right into the thread itself.
Exactly. Researchers are developing yarns that can act as miniature solar cells or generate electricity from movement that's piezoelectric or triboelectric effects.
Okay.
Or from temperature differences, thermoelectric effects, or even store electrical energy, like a tiny battery or a supercapacitor, all within the yarn format.
How do they make these? You mentioned coating.
Yeah, coating is a big part of it. They apply functional materials to the yarn surface or integrate them using processes like dip coating, which is common, or more advanced methods like electrospinning or chemical vapor deposition, CVD.
What's the main challenge with those coating methods? Must be tricky on a flexible yarn.
It is. The coatings need to be incredibly flexible and robust. They have to survive being bent, stretched, rubbed during weaving or knitting, and then during wear. That's tough.
Right.
And for any conductive layers within these complex yarn structures, you need very low electrical resistance along the length of the yarn. Achieving that consistently over, meters or kilometers of yarn is really difficult.
Yeah, I can imagine.
Plus, the whole process needs to be scalable. You need to be able to produce long lengths of this functional yarn cost effectively for it to be practical.
Integrating energy storage like batteries or supercapacitors right into the yarn. That sounds like a massive step towards truly self-sufficient wearable tech. No need for bulky batteries, maybe.
It absolutely is. It's a key goal. The source discusses both supercapacitors and batteries being integrated into yarn formats. Supercapacitors are good for delivering quick bursts of power, and they tend to have very long lifetimes.
And they often use carbon materials.
Yes, they typically use high surface area carbon materials like carbon nanotubes, CNTs, or graphene as the electrodes, because they offer good conductivity and that large surface area needed for storing charge.
Carbon nanotubes seem pretty popular for this, reading the source.
They are. They're widely explored in yarn-based supercapacitors. You can arrange them in different structures, parallel, twisted together, or coaxial, where one layer surrounds another. The source mentions one example where carbon nanotubes were wrapped around a metal wire core at a production rate of about 60 meters per hour. That shows people are thinking about scalability.
60 meters an hour, okay. Still maybe not textile industry speed, but getting there.
Right. But it also highlights a key challenge. They tested a knitted tubular supercapacitor made from this type of yarn and found that its ability to store charge its capacitance dropped significantly as the length of the device increased.
Ah, why is that?
It comes back to that resistance issue. The longer the yarn, the higher the overall resistance. And that resistance makes it harder for the charge to be stored or delivered effectively over the whole length of the device. It limits the usable length.
That really drives home how scaling up from a tiny lab sample creates completely new problems you have to solve for real applications. How about battery yarns? Any cool examples?
There's a particularly fascinating one in the source. A cotton yarn-based battery.
Made from cotton.
Yeah, using cotton yarn as the base. And the really unique part, it uses sweat from the wearer as the electrolyte.
No way. Sweat-powered.
Yeah. It uses carbon black and zinc foil integrated into the yarn structure. When sweat is absorbed, it provides the ions needed to complete the circuit and enables the chemical reaction to produce power.
That's amazing for wearables.
The source highlights it as very attractive, for obvious reasons, though it does note that figuring out how to reliably connect multiple battery yarns together to build up voltage or capacity, integrating current collectors, is still a challenge.
Still, sweat-powered clothes. Incredible. How else are these advanced yarns harvesting energy? You mentioned movement.
Right. Researchers are exploring different mechanisms. Piezoelectric yarns generate a small electrical charge when they're mechanically strained or bent.
Like from walking or moving your arm?
Exactly. The source gives an example of a specific polymer yarn, PVDF, woven into fabric straps. They could generate voltage from movement, but the actual power output was quite low in that case.
Low power, okay. What else?
Another approach is triboelectric yarns, or TNJs, triboelectric nanogenerators. These generate charge from friction, basically, when different materials rub against each other or separate, like static electricity, but controlled.
Okay.
An example mentioned is a special single electrode yarn woven into fabric that generated a surprisingly high voltage, like 40 volts, just from periodic mechanical force being applied.
40 volts is a lot. What about temperature differences, like body heat versus the outside air?
That's thermoelectric harvesting, using the Seebeck effect. Standard thermoelectric generators are rigid blocks, totally unsuitable for textiles. Right.
But researchers are making flexible thermoelectric yarns. For example, using carbon nanotubes again, but with special coated sections along the yarn. These can generate power from a temperature gradient, a difference in temperature across a piece of fabric made from them.
And solar power. Can you really make a solar cell in a yarn?
People are definitely trying. Photovoltaic yarns convert light into electricity. One example in the source involves coating a yarn with perovskite material. Perovskites are used in some high-efficiency, though sometimes less stable, solar cells.
But how well does that work in practice? On clothing?
While the source notes significant challenges, these coated yarns can be easily damaged by abrasion during the weaving process itself, which hurts their efficiency.
Yeah. Rubbing against other threads?
And even if they survive weaving, their performance in a real garment is affected by partial shading. Part of the garment is in shadow, part is in sun. That significantly reduces the overall output. It's a practical hurdle.
Makes sense. Beyond energy, are there other advanced functions being built into yarns? Oh, yeah. Things like strain-sensitive yarns that change their resistance or capacitance when stretched. You can use those to sense body movement or deformation of the fabric.
Like for motion capture?
Could be, yeah. And also electroluminescent yarns that actually emit light when electricity passes through them.
Light up clothing.
Exactly. And even tiny polymer light-emitting diodes, PLEDs integrated onto single filaments. For these more complex functions, the source points out that developing very precise coating methods, like slot die coating, is important. It gives you better control over the thickness and uniformity of the multiple layers needed compared to just dipping the yarn.
Okay, so that's a fascinating look at building functionality right into the yarn itself. The other major approach discussed is applying functional materials onto the fabric surface, often using printing or coating.
Right. This is sometimes called solution processing, because you start with the active electronic materials formulated as liquid inks or pastes.
Like screen printing ink, but with electronic properties.
Pretty much. You can then apply these formulations directly to the textile surface using methods borrowed either from the traditional textile printing industry or from the field of printed electronics. It's attractive because it can potentially be low cost and more easily integrated into existing large-scale textile production lines.
What kind of inks or pastes are we talking about here? What's in them?
Well, they contain the specific functional materials needed for whatever electronic device you're trying to make. So conductive materials are common inks containing silver nanoparticles or carbon materials like graphene or carbon black or conductive polymers.
There's the wires and electrodes.
Exactly. Then you have dielectric materials, which are insulators used for capacitors or just isolating layers. And you can have piezoelectric or piezoresistive materials formulated into inks for making printed sensors.
And I guess you need other stuff in the ink, too.
Oh, yeah. Crucially, these formulations also contain additives, binders, solvents, viscosity modifiers that control the ink's properties. They make sure it flows correctly for the chosen printing method, adheres well to the fabric fibers, and cures properly.
Okay, so for covering large areas of fabric with these functional materials, what methods are typically used?
Dip coating and spray coating are common for applying materials across the full width of a fabric roll, for continuous processing.
Just dunking it or spraying it?
Essentially, yeah. Dip coating has been shown to work at pretty high speeds, like 150 meters per minute, for applying graphene coatings in one example. Spray coating is also versatile, used for things like dielectric layers or even applying the different layers needed for solar cells.
Solar cells printed directly onto fabric.
People are working on it. The source notes, though, that applying these very thin film devices like solar cells directly onto a typically rough, textured fabric surface often requires putting down a smooth planarization layer first.
To make it flat.
Right. And some of the processes involved, especially for certain types of solar cells, might require high temperatures, like 400 degrees Celsius, which could damage many common textile fibers like cotton or polyester. Though lower temperature processes, maybe around 150 Celsius for organic solar cells on polycotton, are also being developed.
Okay, so that's for large areas. What about creating specific electronic patterns on the fabric, like printing circuits?
Screen printing is probably the most common method described in the source. And that makes sense because it's already a workhorse in the traditional textile industry for printing graphics and patterns on T-shirts, things like that.
Right, like putting a logo on a shirt.
Exactly the same principle. You push a viscous paste, your functional ink, through a fine mesh screen that has a stencil pattern blocking parts of it. It forces the ink onto the fabric only where the stencil allows.
And it's good because
it's repeatable, relatively low cost, especially once you have the screen made, and it's suitable for printing both small detailed patterns and large solid areas.
What if people screen printed onto textiles, electronically speaking?
All sorts of things. Or the source gives examples like screen printing conductive electrodes for medical sensors like biopotential monitoring or muscle stimulation patches. They've screen printed components of textile batteries like zinc-ion batteries, piezoelectric layers for pressure sensors, thermoelectric materials for generating power, and even complex multi-layer structures like an entire electroluminescent watch display screen-printed layer by layer directly onto fabric.
An entire display. Wow. What about inkjet printing, like my desktop printer?
Similar concept, yeah. Inkjet printing is a direct write method. You can put patterns straight from a digital computer file without needing a physical mask or screen.
So more flexible for custom designs?
Potentially, yes. It uses low viscosity inks that are jetted through very fine nozzles onto the fabric. It's great for precise patterns, but it typically produces much thinner layers than screen printing.
Thinner means maybe less durable.
That can be a concern, yeah. Thinner layers might be less mechanically robust, especially on a flexible textile. Inkjet has been used for printing conductive paths. Antennas, the source mentions, a 2.4 gigahertz textile antenna example, and discusses its efficiency and various types of sensors.
Any breakthroughs with inkjet inks mentioned?
Yes, a significant development highlighted is the use of particle-free reactive silver inks.
Particle-free. I thought conductive inks use tiny metal particles.
Many do, and that can cause problems like nozzle clogging and maybe imperfect bonding between particles and to the fibers. These reactive inks are different. They contain silver compounds dissolved in the ink. When printed and cured, the silver compounds react and deposit silver atoms directly onto the fibers, forming a continuous, highly conductive coating.
So it's like plating the fibers in place.
Kind of, yeah. This approach gives much higher conductivity and significantly improved durability because the silver coating is better integrated with the textile fibers. It's been used successfully for making durable textile heaters, and it also solves that annoying nozzle clogging problem.
That sounds like a big step. What about dispenser printing?
Dispenser printing is another direct write method, often using a syringe-like system to push out the ink. It's good because it can handle a much wider range of ink viscosities than inkjet, from thin liquids to thick pastes, and it can print thicker lines or dots.
So better for some things than inkjet.
Maybe for things needing thicker layers, like robust interconnections or printed heaters. It's generally slower than screen printing or high-speed inkjet, though. The source mentions its use for printing entire multi-layer electroluminescent lamps and also notes the importance of carefully defining the print path to ensure the deposited material is even.
Are there other printing methods mentioned?
Briefly, aerosol jet printing is mentioned. It's contactless, good for curved surfaces, but seems mostly used on fibers, not direct to fabric yet, and high-volume industrial methods like flexography or gravure printing.
Like for printing newspapers or packaging?
Exactly. They're very high speed but have high setup costs, often use solvent-based inks, which raises environmental concerns, and aren't widely used in e-textiles yet, maybe due to the specific ink requirements and smaller production volumes currently.
What about ways to coat just the fibers you want, selectively?
That's where selective metallization comes in, often using something called electrolysis deposition.
Electrolysis deposition.
Okay. The idea is you first apply a catalyst material only to the specific areas of the fabric where you want the metal. You could print this catalyst using screen printing or inkjet. Then, you dip the whole fabric into a chemical plating bath containing metal ions, like copper or gold. The metal only deposits and plates onto the fibers where the catalyst is present.
So you get conductive fibers only in your pattern.
Exactly. And because it coats the individual fibers rather than creating a solid block of printed material on top, it can help the textile retain more of its flexibility and breathability and can achieve very low electrical resistance.
And one last approach mentioned was printing onto a separate film first.
Right. You can print your electronic circuit onto a thin, flexible polymer film substrate. This can actually be easier and allow for finer feature sizes, higher resolution, than printing directly onto a bumpy, fibrous textile surface.
And then you stick the film onto the clothes?
Pretty much. You then laminate or bond that printed film onto the textile, often using heat and pressure-sensitive adhesives. This is useful for more complex circuit layouts.
Yeah.
The downside is that the resolution for actually attaching tiny components to the circuit on the film can still be limited, and the laminated film itself might affect the textile's breathability or feel in that area.
Makes sense.
The source also notes that sometimes, instead of printing, simply cutting patterns from pre-made conductive fabrics and then laminating those shapes onto the base textile can be more effective or efficient, especially for things like antennas, where getting good performance might be easier with a solid conductive fabric patch than a printed one.
Okay, so we've covered adding function to yarns and printing or coating onto fabric, but integrating the actual brains, the complex, often rigid semiconductor chips like microprocessors or advanced MEMS sensors, that seems like a totally different challenge.
It absolutely is. This is consistently highlighted as one of the most significant challenges in the entire field.
Why is it so hard?
Because standard electronic chips are typically made from silicon, which is rigid and brittle. Textiles, by their nature, are flexible, stretchable, dynamic. The point where you connect a rigid chip to a flexible textile path becomes a major stress concentration point.
Like bending a paperclip back and forth.
Exactly. It's a frequent point of failure, especially with the constant movement during wear and particularly during washing cycles.
So how have people tried to tackle this over time? What's the evolution been like?
Well, the source outlines it. Early attempts were pretty basic. trying to weave conductive fibers into a simple bus structure to connect things, or manually creating textile circuit boards. And then you have those hobbyist kits we mentioned, where you just sewed on standard rigid boards like the lily pad.
But those weren't really practical for mass production or comfortable wear, right?
Not at all. They weren't scalable, durable, or comfortable enough. So researchers started looking at how to attach standard components more directly.
Can you just stick a normal chip onto fabric?
You can attach some simpler lumped components like inductors or diodes directly. And the source notes that sometimes these textile integrated versions can even perform better than rigid ones for specific functions like RF energy harvesting rectennas. But overall, the durability of standard components directly on fabric is generally poor.
So what's a more common approach now for attaching standard chips, like SMDs?
A more common approach involves bonding standard surface mount devices, or SMDs, directly onto conductive pads on the textile. This often uses special conductive adhesives that are cured, maybe by heat or pressure.
Does that work well? How durable is it?
It works, but durability is still the main issue. While used encapsulation techniques, basically coating the component and connection points in a protective polymer can help them survive a limited number of washes.
Like how many?
One study mentioned in the source saw encapsulated components survive up to 10 standard washes with only a small increase in electrical resistance, which is progress, but maybe not enough for everyday clothing yet.
And it probably makes the fabric stiff there.
Exactly. Bonding these rigid components inevitably creates rigid spots on the fabric, which impacts comfort and flexibility. And eventually, with repeated flexing and washing, those connection points tend to fail.
Okay, so what about making the connections between components flexible, even if the chips themselves are rigid?
That's another strategy. Techniques involve embedding ultra-thin silicon chips, or standard components, within flexible polymer materials, like silicone.
So the chip is floating in rubbery stuff?
Kind of. And then you have stretchable conductive traces connecting these components, often designed like meandering copper lines to accommodate stretching. This creates rigid islands of components within a flexible matrix.
Does that solve the problem?
It improves overall flexibility compared to just sticking a single large rigid board on. But the flexible material itself, like silicone, can reduce the textile's natural properties, like breathability, and you still have the challenge of how to robustly attach this entire composite structure to the underlying textile.
Right. What about embedding the components right into the yarn structure itself? We touched on this earlier, the E-yarn idea.
Yeah, the E-yarn concept. It involves attaching tiny electronic components, simple things like LEDs or temperature sensors, usually to thin conductive wires inside a yarn structure.
And then protecting them somehow.
Often, yes. They're typically protected by encapsulating them in a small resin pod, like a tiny bead along the yarn. And then the whole thing is covered with standard textile fibers so it looks and feels more like a regular yarn.
That sounds pretty integrated. What are the limitations?
It's great for creating long lengths of yarn with distributed, simple functions, but it's generally limited to simple components that only need 2 electrical connections. You can't easily put a complex microprocessor in there yet, and the size and stiffness of that resin pod can still affect the yarn's feel and comfort.
How washable are these E-yarns?
It depends. The source notes that washability seems related to the size of the encapsulated device. Smaller pods, maybe around 1.5 millimeters in diameter, survived up to 25 wash cycles in one study, while larger ones failed sooner. There's a commercial example called Primo 1D E-thread that embeds an RFID chip this way.
25 washes is better. Okay, and then there's the idea of flexible filament circuits. This sounds like maybe the most advanced approach.
It really seems to be a significant step forward, based on the source. This involves fabricating potentially complex electronic circuits on long, extremely thin, flexible substrates. These filament-like circuits can then be integrated directly into the textile structure, maybe by weaving or knitting them in like a special yarn.
So the circuit itself is long and thin and flexible.
Exactly. Early attempts mentioned involved simply weaving plastic strips with components attached onto them into fabric, but the components were often left exposed and failed quickly, especially with washing.
So what was the breakthrough?
A major advance came from researchers at the University of Southampton with their Sea Fleet platform. They developed a process to attach bare silicon chips, actual microprocessors, complex MEMS sensors, not just packaged components onto circuits that were patterned on super-thin, flexible polyamide films.
Polyamide, like Captain Tape, that stuff is flexible.
Exactly. These circuit films are tiny and highly flexible, allowing them to be integrated almost invisibly within yarns or woven directly into fabrics.
But how did they make them durable, especially against washing?
That was the key innovation. They developed a novel, conformal polymer film encapsulation technique specifically for these flexible filament circuits. This thin coating provides incredible protection for the bare chips and the fine circuit traces.
How good was the protection?
The source highlights this as a major result. This encapsulation allowed complex circuits, including RFID chips with their antennas, to survive up to 50 standard machine wash and spin dry cycles.
50 washes. That's huge. That gets us much closer to practical, everyday smart clothing that you don't have to baby.
It really does. It's a huge leap in durability compared to most previous methods described.
Any other examples of this flexible filament approach?
Yes, MIT also demonstrated a similar concept. They created flexible filament circuits that had small, rigid areas where components were mounted, connected by stretchable interconnects. They integrated these specifically into pockets sewn into knitted garments.
Integrated into pockets? How did they connect them?
They connected these filament circuits in series, using a standard communication protocol like I2C, and linked them to a single, larger detachable electronic module. This module may be snapped out of the garment, contain the main processor, Bluetooth radio, and battery.
Ah, so keep the bulky stuff detachable, but integrate the sensors flexibly.
Exactly. The source notes that this kind of localized approach, concentrating the complex electronics in one area and using flexible filaments for distributed sensing, minimizes the impact on overall wearer comfort, especially if you use wireless communication from that central module.
Okay, so we have these amazing ways now to put functionality in yarns, print on fabric, and even integrate complex chips using these flexible filament circuits that can survive washing. But bringing all these different pieces together in a working system requires reliable electrical connections between them. And it seems like this interconnection challenge is still a massive bottleneck for the whole field.
It absolutely is. You said it, a massive bottleneck. Think about it. You need to reliably connect power sources to modules, modules to sensors, sensors maybe to output, devices like LEDs or haptic feedback.
All across a substrate that's constantly bending, stretching, and getting thrown in the wash.
Precisely. Traditional rigid connectors from the electronics world just won't work everywhere in that dynamic environment.
So what kind of connections are being used or explored for E-Textiles?
Well, they can generally be categorized as either permanent or detachable. Permanent connections might involve using conductive adhesives or even stitching with conductive thread.
Sewing connections.
Yeah, it's explored. Detachable connections might use things like conductive snaps, like on clothing, or specialized zero insertion force connectors adapted for textiles, or simple push-fit contacts where conductive pads press together.
But are these solutions really good enough?
That's the problem. The challenge is that most of these existing methods are either directly borrowed from standard electronics, which assumes rigidity, or they're adapted from clothing fasteners, which weren't designed for reliable data transfer.
And this is where the source really flags a critical issue, isn't it?
Yes, it's stated very clearly. The source emphasizes that there is currently a significant lack of commercial connectors that have been specifically conceived and designed exclusively for widespread e-textile use.
Nothing purpose-built.
Largely no. Not readily available commercial solutions designed ground up for the unique demands of textiles. This absence of scalable, durable, textile-specific connectors is seen as a major barrier preventing more complex e-textile products from reaching the market successfully.
Why is it so hard to design a good textile connector? Is it that rigid, flexible interface problem again?
That's exactly it. A connector, by its nature, typically involves a relatively rigid element interfacing with the flexible textile conductor path. This transition point inevitably creates mechanical stress concentrations.
The bending focuses right there.
Right. And that's where failures often occur, especially under the constant bending, stretching, and torsional forces during wear, and the abrasion and chemical exposure during washing.
Are people trying to mitigate that stress?
Yes. Researchers are exploring ways to design the conductive patterns near the connection point differently, maybe making them wider or using specific meandering shapes, or using intermediate materials called interposers to create a more gradual transition in stiffness between the rigid connector and the flexible textile. These things can improve durability, but they also add complexity and cost to the manufacturing process.
So in practice, how are most current commercial e-textiles that are on the market handling connections?
From what the source describes, many of today's products, especially simpler ones, tend to rely on having a detachable, rigid electronic module, the part with the battery and maybe the main chip that you absolutely must remove before washing. These modules often connect to the textile, perhaps to simple conductive patches or electrodes woven or printed into the garment using very basic methods like pressure fitting. Metal contacts on the module just press against conductive pads on the fabric.
But that only works for simple connections, right?
Exactly. These pressure fit connections are usually very limited, maybe just providing power, 2 connection points, or connecting to 1 or 2 simple sensors. They're generally insufficient for more complex systems that might require multiple data lines, power distribution to many different components throughout the garment, and so on.
So the takeaway is clear. Developing scalable, robust, flexible, and washable interconnection solutions is absolutely critical for the field to move beyond simple demonstrators and enable widespread adoption of more complex e-textiles.
That sums it up perfectly. It's a major engineering hurdle that still needs significant breakthroughs.
All right, let's shift gears now and tackle the really big picture issue, the one you mentioned right at the start, the elephant in the room, sustainability. E-textiles inherently combine electronics and textiles, and both of those industries individually already have massive environmental footprints and huge waste problems.
This is arguably the most critical long-term challenge facing the field, especially if e-textiles are to become widespread. Merging these two problematic waste streams creates composite materials, textiles intimately combined with metals, plastics, adhesives, electronic components
that are incredibly difficult, maybe impossible, to recycle using the existing infrastructures we have for either textiles or electronics alone.
Exactly. They fall between the cracks. And this dramatically increases the risk of the entire product, the smart garment, ending up in landfill or incineration at the end of its life.
And the potential scale of this new waste stream could be enormous, couldn't it? Even with relatively low market penetration initially.
That's what a simulation study cited in the source suggests. They estimated that even if just a small percentage, like 1% of the target market in the EU, adopted a single type of e-textile product, they use the health monitoring shirt as an example, it could generate roughly 1 kiloton of mixed electronic textile waste per year, just from that one product type in one region at low adoption.
1,000 metric tons. Wow. If e-textiles become truly ubiquitous like some envision, the waste problem could become absolutely immense.
It could dwarf the current issues if not handled correctly from the start.
And we have to remember, the fashion and textile industry's environmental record isn't exactly stellar to begin with, is it?
No, it's widely criticized. It's resource-intensive, huge amounts of water, energy, chemicals used in dyeing and finishing. It's often driven by fast fashion, leading to overproduction and garments being discarded quickly. And global recycling rates for clothing are shockingly low.
What did the source say? Less than 1%?
Yeah, less than 1% of textile waste globally is recycled back into new clothing. Most ends up landfilled or incinerated. Now, add electronics into that mix.
What does electronics?
Well, you add potentially toxic materials, like flame retardants often used in printed circuit boards. You add complex laminated structures that are hard to separate. And you introduce nanomaterials, like those carbon nanotubes or silver nanoparticles, whose long-term environmental fate and potential impacts aren't fully understood yet.
So it sounds like the sustainability conversation is becoming absolutely central, maybe unavoidable, as e-textiles start moving towards serious commercialization.
It has to be. And it is. There's a growing global push, including new legislation and regulations, towards a circular economy model.
Moving away from take-make waste.
Exactly. Moving away from that linear approach towards models that prioritize keeping products and materials in use for longer through durability, repair, reuse, remanufacturing. The EU, for instance, is mandating the separate collection of textile waste across member states, starting in 2025, which will highlight the scale of the problem.
And the source makes a really powerful point about the role of design in all this.
Yes, it repeats a common statistic, but it's crucial. Something like 80% of a product's total environmental impact is determined during the design phase, before anything is even manufactured.
So decisions made early on have huge consequences later.
Absolutely. For e-textiles, applying circular design principles means consciously designing these products not just for function and aesthetics, but also for longevity, making them easy to repair if something breaks, enabling components to be reused or remanufactured, and finally, making the entire product easy to disassemble at the end of its life so materials can be recovered for recycling. And critically, thinking about all of this before the product even reaches the end of its first useful life.
But there seems to be a fundamental tension here, doesn't there? On one hand, the goal is often seamless, invisible integration, making the electronics disappear into the fabric. But on the other hand, for sustainability, especially recycling, you need to be able to easily separate the electronic parts from the textile parts. Those goals seem opposed.
That is the key conflict the source highlights repeatedly. The drive for seamless, aesthetically pleasing, highly integrated design often clashes directly with the need for easy disassembly and material recovery at end of life.
So designers have a tough balancing act.
They do. Designing for end-of-life processing DFD, design for disassembly has to become a primary consideration right alongside performance and cost, not just an afterthought.
What are some of the key design principles for more sustainable e-textiles?
The source outlines several. Careful material selection is key, prioritizing materials that are inherently more sustainable, perhaps bio-based like cellulose or earth-abundant, or known to be easily recyclable, while minimizing hazardous substances. Choosing manufacturing processes that use fewer resources, generate less waste, and have lower emissions is also important. Considering the energy consumption of the device during its use phase matters too. And then building in features that facilitate repairability and recyclability.
The source mentioned a 4R framework.
Yes, repair, recycle, replacement of components, perhaps modularly, and reduction of materials used overall. It's about extending the product's useful life as much as possible before you even have to think about recycling.
And what's the reality of actually recycling e-textiles today? Can it even be done?
Well, recycling should always be the last resort, after reuse and repair options are exhausted. But even then, the source points out that specific research into effective e-textile recycling methods is still quite limited.
What's the main difficulty?
The biggest challenge is sorting and separating the complex mix of materials. How do you efficiently separate tiny electronic components or thin metallic coatings from textile fibers? How do you deal with adhesives? How do you recover potentially valuable metals without degrading the textile? And what about those nanomaterials?
Yeah, tricky.
There's a lack of clearly defined, scalable recycling processes and the necessary industrial infrastructure to handle this new type of waste. Eco-design standards exist for general electronics, like WEEE regulations, or for textiles, but applying them effectively to these hybrid composite materials is still an area under development.
Okay, so given these enormous sustainability challenges, what are the early steps being taken? What progress is being made towards making e-textiles more sustainable, even if we're not there yet?
The source acknowledges that we're definitely not at the point of having widely available, truly fully sustainable e-textiles yet. It's early days. But progress is being made on several fronts.
Like materials?
Yes, one major focus is on materials. Researchers are exploring the use of natural fibers, like cotton, hemp, or cellulose as the base textile, combined with more sustainable conductive materials or coatings, maybe using conductive polymers or carbon-based materials like graphene derived from biomass, instead of relying solely on synthetic polymers and energy-intensive or less environmentally friendly metals.
Are there downsides to using natural fibers?
Sometimes. The source notes that incorporating conductive materials or coatings can sometimes compromise the natural fiber's mechanical strength or other properties, and even with more eco-friendly conductive materials like nanoparticles, there are still concerns and ongoing research about their life cycle impacts and potential release into the environment.
What about that design for disassembly idea? Are there practical examples?
Yes, that's a very active area. Researchers are exploring specific design techniques, for instance, using particular embroidery patterns that might allow embedded components or conductive threads to be more easily pulled out or removed later, or designing knitted structures that can be easily unraveled to separate conductive yarns from non-conductive ones.
Modularity seems key, too.
Definitely. Modular design, where the main electronic parts, especially things like batteries or complex sensor modules, are designed to be easily detached from the garment, is a very promising route. The source mentions the commercial function garment system using magnetic connectors as an example. This modularity not only helps with sustainability by allowing easier separation, but it also enhances washability. You remove the module. Repairability. You can swap out a faulty module, and potentially allows for upgrading the electronics without discarding the whole garment.
That makes a lot of sense.
Another clever approach mentioned involves using specific types of adhesives to attach components, like a UV curable adhesive. The interesting part is that this adhesive can later be softened or dissolved by soaking the connection point in a solvent like acetone, allowing the electronic components to be carefully removed, potentially recovered, and maybe even reused in another device. And studies showed components attached this way could still survive washing before disassembly.
Recovering and reusing components, that's very circular.
Hmm.
What about the manufacturing processes themselves?
Yes, there's progress there too. For printed E-Textiles, there's a push towards developing more sustainable inks and solvents using water-based formulations instead of harsh organic solvents, for example. Also, applying the functional inks just as a thin coating onto the textile surface rather than saturating the whole fabric can significantly reduce the amount of material needed.
And additive processes.
Right. Additive processes like inkjet and dispenser printing, which deposit material only where it's needed, are inherently less wasteful than traditional subtractive manufacturing methods used in conventional electronics, like etching away copper from a board.
And finally, addressing the power source seems absolutely critical for sustainability, right? Conventional batteries are a big e-waste problem.
Absolutely. Relying on standard, rigid lithium-ion batteries that have to be removed for washing and eventually discarded really undermines the whole seamless integration goal and contributes significantly to the e-waste burden.
So the solution is integrated power.
That's the long-term vision. A key direction for both better integration and improved sustainability is developing energy storage solutions directly within the textile itself, whether that's through those yarn-based batteries and supercapacitors we discussed earlier, or through printed battery structures.
Any promising chemistries mentioned besides lithium?
Yes, the source highlights the promise of zinc-ion battery chemistry. Zinc is much more abundant and generally considered less toxic and safer than lithium.
Yeah.
And zinc-ion batteries have already been demonstrated in various textile formats. There was even a fascinating prototype mentioned that used activated carbon derived from cotton textile waste itself as an electrode material for a zinc-air battery.
Using waste to make a battery, that's really closing the loop.
It's a great example of circular thinking, yeah.
Okay, so pulling this all together then, this deep dive really reveals a field with incredible potential, smart clothing doing amazing things, but also, wow, there are still some significant mountains to climb, both technically and, maybe even more importantly, sustainably.
Yes, the source makes that very clear. Technologically, hurdles definitely remain. We still need better, more robust materials. We need manufacturing methods that can truly scale up to match the volumes and costs of the traditional textile industry. We need more seamless ways to integrate complex electronics. We need improved power generation, storage, and management solutions integrated into the textile. And, as we discussed at length, we desperately need reliable, flexible, and durable interconnections.
And prototypes often just solve one piece of the puzzle, right?
Exactly. Current demonstrators often show success in one specific area, a great sensor yarn, a washable connection, but rarely integrate all the necessary pieces into a fully functional, durable, scalable, and sustainable system yet.
And beyond the purely technical stuff, what other challenges does the source point out?
There are significant non-technical challenges too. Things like user skepticism or low awareness can mean low initial adoption rates. That leads to low production volumes, which in turn prevents the cost reductions that only come with mass manufacturing. It's a bit of a chicken and egg problem. There's also often a lack of single companies or even research teams that possess deep expertise across both the textile world and the electronics world simultaneously. It requires true cross-disciplinary collaboration.
And standards. That came up multiple times.
Yes, the source really hammers this point home. The absence of comprehensive standards is identified as a major roadblock holding back the entire industry.
What kind of standards are missing?
Well, the source notes that standards currently exist, maybe, for very basic things like defining conductive fibers or testing yarn conductivity. But we desperately need internationally agreed upon standards for testing methods relevant to e-textiles. How do you reliably test washability, durability under flexing and stretching, electrical performance in a textile context?
Ooh, that's not a rigid circuit board.
Exactly. And crucially, we need standards for waste classification. How do we categorize end-of-life e-textiles? Standards for separation techniques and standards for recycling processes specifically designed for these unique composite materials. Without these clear frameworks and definitions, industry adoption at scale is very difficult because manufacturers lack clear targets for performance, safety, and crucially, end-of-life handling and responsibility.
And the whole sustainability dimension just adds another layer of complexity onto all of this.
It really does. It weaves through all the other challenges. Achieving sustainability requires a holistic view, looking at the entire supply chain and the full product life cycle, from raw material extraction to disposal or recycling. There are often difficult trade-offs to be made between functionality, cost, and choosing the most sustainable material or process options.
And as we said, the recycling methods are poorly defined.
And there's often a lack of clear legislation or economic incentives clarifying who is responsible for collecting and dealing with e-textile waste at the end of its life. It's a complex system problem.
Well, this deep dive has certainly been eye-opening. It's shown the incredible innovation and ingenuity happening in e-textiles, but also the sheer complexity of making them a practical, widespread, and responsible everyday reality.
Absolutely. The source makes it clear that moving forward successfully requires true multidisciplinary collaboration. We need material scientists, textile engineers, electronics designers, chemists, software developers, even fashion designers, and sustainability experts all working together, speaking the same language.
And engaging everyone involved.
Yes, it needs engagement from the entire ecosystem. The researchers developing the tech, the manufacturers figuring out how to scale it, the brands designing products people want, the users providing feedback, and the policymakers setting the rules and incentives.
So if there's one single most critical takeaway from this source that you think our listeners should hold on to, what would it be?
I think it has to be the urgent, critical need for those international standards we just discussed. Clear, agreed-upon standards covering testing methodologies, waste classification, material separation, and especially recycling and end-of-life processing. Providing that infrastructure and framework is absolutely essential for the industry to mature and scale responsibly.
And using tools like life cycle assessment, LCA, seems vital from the very beginning.
Precisely. LCA is the established tool that helps designers and manufacturers move beyond just making assumptions about what materials or processes are green. It allows them to quantitatively assess the actual environmental footprint of their choices across the entire product lifecycle, from cradle to grave, or ideally, cradle to cradle. It's essential for making informed decisions.
Okay, so here's a final provocative thought for you, our listener, to consider, building on everything we've explored today from this source material. As we look towards a future where electronics are integrated more and more deeply into the very fabric of our lives, quite literally, in the case of e-textiles, solving the sustainability challenge isn't just a technical problem for engineers and scientists to figure out. It seems to demand a much more fundamental shift in mindset. A shift for the companies making these smart garments, yes, but also for us as consumers. Can we collectively move beyond the disposable culture that currently plagues both the electronics and the fashion industries? Can we learn to truly value the longevity, repairability, and circular potential of the things we wear and use, especially as they become smarter? Can we embrace a truly circular future for smart clothing?
That really is the multi-trillion-dollar question, isn't it? The answer probably determines whether this technology fulfills its potential responsibly or just adds another layer to our existing environmental problems.